Hello everyone, I'm Norman Wahlberger and welcome to the Algebraic Calculus. In today's lecture we're going to be talking about change of variables and integration by substitution. So this is a standard and important technique for helping us to augment our ability to integrate. And also the actual change of variables formula is really a remarkable aspect of the theory of integration that we've developed, going back I think essentially to Leibniz. So recall that for the Faulhaber derivative, capital D, we have our familiar product rule. Now there's a sort of special consequence of this called the product power rule, that the derivative of p to the n is n times p to the n minus 1 times d of p for a general polynumber p. And I also remind you of the chain rule, that if we define the composition of two polynumbers, say p circle q of alpha is p of q of alpha, then the derivative of the composition p circle q is the composition of the derivative of p with q times the derivative of q. And I remind you that this one here follows from this one here by induction. Okay, once you know how the derivative of the product of two things works, then you can figure out what the derivative of a product of n things works by sort of applying it over and over again. And then to go from here to here, it's a question of looking at p and sort of separating it out. P is a polynumber, so it has all kinds of terms, each of a certain power, and basically applying this formula to each one of those things. Okay, so that's sort of the logical structure of these things. And today we're going to be looking at this chain rule and what happens when we integrate it, what we can extract from that. I remind you that when we derive the integration by parts formula, we combine the product rule with the derivative integral composition theorem. We're going to do the same kind of thing today, but we're going to combine this thing now with the chain rule. So this derivative integral composition theorem tells us what happens if we first integrate and then differentiate. First of all, we get back exactly what we started. That's the identity operation. However, if we do the derivative first and then we integrate, then we almost get back what we started. It's the identity minus I0. That means we have to peel off the constant term of the polynumber that we're starting with. So that's the actual top element just is replaced with 0. Okay, so if we combine this with the chain rule, we get the algebraic integration by substitution formula. Here it is. The Faulhaber integral, capital S, from t to u of this expression, the derivative of p composed with q times the derivative of q, that equals the composition p circle q evaluated from t to u. And why is that? Well, because the chain rule tells us that the derivative of this is exactly what's inside here. So if we take the integral of this, we're essentially getting this thing back minus the identity, minus the zeroth part of it. And we get rid of that zeroth part by evaluating the integral between two different values, t and u, the value at u minus the value at t, then the constant term is disappearing. So that's why we're just getting this p circle q from t to u. That's the integral of this composition. Okay, so for an example, let's calculate the integral from 1 to 3 of alpha times 1 plus alpha squared to the 5th. Now the trick is to kind of arrange this in your mind so it looks like the composition of something with a derivative of the thing that we're composing with. So what we can do here in our minds is to set p equals alpha to the 6 over 6 and q equals 1 plus alpha squared. So now the derivative of q is 2 alpha. That's more or less that term there. And the derivative of p will be alpha to the 5th. And what's appearing here is that derivative composed with q. So it's 1 plus alpha squared to the 5th. Okay, so except for a constant term here, we're almost exactly in the situation of having identified how the terms here correspond to the terms here by a suitable choice of p and q. So this thing is In fact, we're just sort of rearranging it now to make it closer to what we want. So we'll rewrite it as integral from 1 to 3, 1 plus alpha squared to the 5th times 2 alpha now, and we'll multiply by a half here to compensate for that 2 that we've introduced there. Okay. So now we really have this thing here is the derivative of p composed with q. That's exactly what that is. And this term here is the derivative of q. So the algebraic integration by substitution formula tells us that this is going to be, well, the half there, and then this whole thing will be p circle q. So the p composed with q. So that's that inside there. That's p circle q. We're taking q to the 6th power and dividing by 6. Okay, so that's relatively easy. We just plug in 3, we get 1 plus 9, that's 10 to the 6th, minus 1 plus 1, so that's 2 to the 6th. The 6 comes out front with a 1/12 there. That's an example of integration by substitution. And again, this is a purely algebraic thing. It's just at the level of Faulhaber integration, Faulhaber derivatives, just purely in terms of polynomials. All right, now we come to a really remarkable formula, closely related to the integration by substitution formula. This is the change of variable formula that allows us to reparametrize a curve and we still get the same signed area. So it's telling us that somehow the signed area really is associated to the geometrical curve, whatever that is, rather than dependent on the particular parametrization that we've chosen. But we'll see in the examples that it's a little bit more subtle than that. Anyway, here is the formula for polynumbers p, q, and r. If we take the signed area from t to u of the curve defined by p circle r and q circle r, that's equal to the signed area from r of t to r of u of p q. So the original curve, maybe this one here, defined by p and q, and we're going from r of t to r of u, that's the same as this more complicated composition, but evaluated at the more simple bounds of t and u. So this remarkable formula suggests that reparametrizing a curve does not actually change signed areas. And it's essentially an observation, a key observation of Leibniz. Okay, so now I want to illustrate the change of variable formula with a series of examples, starting with some simple ones and then working our way up. And as we go, we're going to see that what exactly a curve is going to be called into question a little bit. Okay, so we're going to have to be flexible about our understanding of the geometry that goes with the algebra. So let's start with a simple case, essentially a parabola, where p is alpha and q is alpha squared. Okay, so that's the curve usually called y equals x squared. And we're going to compose these with 1 plus 3 alpha, call that r. So now we have 1 plus 3 alpha squared. And we're going to agree that we're going to go from 0 to 1. When alpha is 0, we have the point 1, 1. When alpha is 1, we have the point 4, 4 squared, or up there, 4, 16. So we're talking about this portion of the curve. So let's calculate its signed area. Signed area from t to u of p circle r, q circle r. So the compositions are 1 plus 3 alpha and 1 plus 3 alpha squared. Okay, we're composing 1 plus 3 alpha with both of these. Okay, so this is a signed area. We know how to compute that. We can use the fundamental theorem of algebraic calculus, saying that we can calculate it by 1/2 of the Faulhaber integral from 0 to 1 of the first term times the derivative of the second minus the second times the derivative of the first. Okay, the derivative of 1 plus 3 alpha squared is, well, there'll be 2 times 1 plus 3 alpha with another 3. So there will be then 1 plus 3 alpha squared with a 2 and also a factor of 3 appearing. And over here, the derivative of this is just 3. So we get 3 times 1 plus 3 alpha squared. And these combine to give us 3 times 1 plus 3 alpha squared. Okay, this is easy to integrate. The integral is 1 plus 3 alpha all cubed over 3. You can check that the derivative of this is what's inside here. And we're going from 0 to 1, so we substitute 1, at which point we get 4 cubed. Substitute 0, we get 1 cubed. This thing comes out denominator of 6 there. So altogether we get 63 over 6 for the signed area of this thing, computed from this point of view, when we're thinking about it as being expressed this way with parametrization 1 plus 3 alpha, 1 plus 3 alpha squared from 0 to 1. Now, on the other hand, if we just sort of stick with the curve PQ, alpha, alpha squared, now we have to go from R of t to R of u. R of t, R of 0 is 1, R of u is 4. So it's the signed area from 1 to 4 of alpha, alpha squared. So it's the same curve sort of segment geometrically, but it's parametrized in a different way. And this integral is very easy to do. It's just 1/6 because the fundamental formula, 2 minus 1 over 2 times 2 plus 1, that's 1/6. And then there's the power of 3, so it's 4 cubed minus 1 cubed. And we get the same answer. So the long and short of it is that from going from here to here, we've reparametrized the curve. The calculation of the integral is then different, but you end up with the same answer. So the signed area is, at least in this case, independent of the parametrization. At least we've been able to change from this parametrization to this one, and the signed area has not changed. Now let's have a look at a little bit more sophisticated example of this change of variables formula. So we've got a curve that looks like this now, given by p equals alpha cubed and q equals 4 plus alpha squared. And the change of variables is given by r equals 1 minus 2 alpha plus alpha cubed. We're going to go from t equals minus 2 to u equals 2. So here are the two expressions that we want to prove equal. S from r of t to r of u of pq, and s from t to u of p circle r, q circle r. So let's have a look at the first one. So p and q are in here, and r of t, if you plug r of minus 2 inside there, you're going to get minus 3. And when u is 2 plugged in here, you get value 5. So we're going from minus 3 to 5, integrating alpha cubed 4 plus alpha squared. So by linearity, this is really two different ones. It's alpha cubed together with 4, and also alpha cubed together with alpha squared. So we just use the fundamental formula quite simply. The first of them, there's a factor of 4 coming out, and then the exponents 0 and 3. So we get 0 minus 3 and 2 times 0 plus 3. And we have to multiply that by 5 cubed minus minus 3 cubed. And then the other term involving alpha cubed and alpha squared, well, now the constant term will be 2 minus 3 over 2 times 5. And we have to multiply by 5 to the 5th now, because the sum of the powers is 5. So 5 to the 5th minus minus 3 to the 5th. And all of this evaluates to minus 3,204 divided by 5. So with the original parametrization of alpha cubed and 4 plus alpha squared, we're going from here all the way up to actually an endpoint of 125. That's 5 cubed. So we're talking about the signed area determined by these two lines here and the curve. Right, and now the other side of the change of variables, signed area from t to u of the composition p circle r and q circle r. Okay, r is this expression. There it is cubed, that's the p function, and here is 4 plus that quantity squared. That's inside, more complicated, but the bounds are a little bit simpler. Okay, so we can apply the fundamental theorem. It's this quantity here times the derivative of this one minus this quantity times the derivative of this one. And then, well, it's a bit of algebra to work this thing out. And then you evaluate it from minus 2 to 2. And you have to integrate it from minus 2 to 2. And there's a 1/2 in front. And it turns out that you also get minus 3,204 over 5. Now, what makes this a little bit interesting is that if we follow this second parametrization, it's no longer a bijection. Okay? So what happens to the actual point if we actually substituted alpha in here and ran from minus 2 to 2? What would happen is that it would go up like this, but because of this cubic is kind of doing something like this. So what happens is that the point actually moves along certain ways and then doubles back before it proceeds to the end point. Right? So we are no longer talking about a bijection, no longer talking about reparametrizing just the curve itself. We're actually traversing it and then looping back and so on. So that's actually a situation that's outside the realm of application of a lot of traditional change of variables formulas. This would not be covered. But it is covered here, and it is, in fact, working out very beautifully. And now with our last example, I want to show you a phenomena that goes beyond the bounds of the previous ones and suggests to us that maybe we need to think more flexibly about what a curve actually is. So here the example is p equals alpha cubed and q equals alpha. That's relatively simple, just this cubic curve, alpha cubed alpha. And we're going to compose it with 1 plus t alpha minus alpha squared from the bounds t equals minus 1 to u equals 2. Okay, so the one side of the equation is s from r of t to r of u of pq. So we're going from r of t. When t is minus 1, plug that in there, we're going to get minus 2. And when we plug in 2, we get 1. So we're going from minus 2 to 1, just integrating alpha cubed and alpha. That's signed area. Well, that's just a simple application of the fundamental formula. So the difference is minus 2 divided by 2 times the sum, 2 times 4. And then we're going 1 to the 4th minus minus 2 to the 4th. 4 because the 3 plus 1 is 4. And we get 15 over 4. Maybe we'll circle that. Okay, so that's relatively easy. We're imagining a point moving along. So when we're at minus 2, we're over here at minus 8 and minus 2. And then as alpha increases up to 1, we're just increasing steadily until we get to the point 1, 1. So this thing here is talking about the projectile going from here along the curve nicely to the end point there. Okay, now we make this change of variable. We compose these two functions with this quadratic function r, which is 1 plus t alpha minus alpha squared. Its graph is like an inverted parabola. Okay, so what happens there now? So now we're just going from t to u, so signed area from t to u from minus 1 to 2 of, okay, here's r cubed, because we're composing with p, and here is r to the 1. Okay, so we calculate this. This is going to be 1/2 of the Faulhaber integral from minus 1 to 2 of this quantity times the derivative of the second one minus the second one times the derivative of the first one. And when we calculate that, not surprisingly, we get 15 over 4 as the formula tells us we should. But what's interesting now is that here's this graph of y equals 1 plus 2x minus x squared from minus 1 to 2. And what you can see is that it doesn't just proceed between the values of minus 2 and 1. It actually exceeds the value. It goes up to the point 2 when x equals 1. So when x equals 1, we have 2 minus 1 plus 1. We're actually at the point 2 there. So what's happening there is that if we look at this parametrization here, okay, as the parameter is going from -1 to 2. Yes, we go from here to here, but we do so in a rather roundabout way. When we are at the point alpha equals 1, then inside here we're going to get 2 cubed. That means that the x-coordinate is actually 8. So we're going here along the parameters, ticking along, and by the time we're at the parameter 1, the point is actually out here. And then it comes back to here. So we're actually traversing a path which goes beyond the original curve that we are considering. And this is part of the integration that's being done here. This thing is integrating the curve that goes like this, out to there, and comes back. So it's not just that we're reparametrizing that actual geometrical segment there. We are somehow able to access other parts of this curve. So the idea of a segment becomes a little bit more ambiguous here. But in any case, the formula is purely algebraic. Okay, so what the statement is, it works no matter which way things are oriented, no matter what the parameters are doing. It's just an algebraic formula, and it's really a remarkable thing. So now the question is, why is it actually true? So I think the proof that I'm presenting to you now is a novel one. It's different from the ones that you usually find. So often arguments in this direction involve sort of geometrical thinking in terms of little comparisons of small infinitesimal pieces here and here under a transformation. Sometimes Leibniz's dx over y times dy over dz equals dx over dz kind of argument is used. The argument here is entirely algebraic. Okay, we're only dealing with polynomials, and everything is really algebraic. So it's a different kind of argument. So we want to prove this formula, and we'll start with this side, signed area from T to U of P circle R, Q circle R. So the fundamental theorem tells us that we can evaluate this in terms of 1/2 Faulhaber integral from T to U of what? Of this first thing, which is P circle R, times the derivative of the second, minus the second times the derivative of the first. Fair enough. And now we're going to rewrite this because involved here are derivatives of compositions. And the chain rule tells us how to evaluate those derivatives. So instead of dq circle r, we now have right here d of q circle r times dr. That's what the chain rule tells us this is equal to. And over here, the dp circle r is replaced with d of p circle r times dr. Okay, now next line, we're still taking 1/2 Faulhaber integral from t to u. And now we look at this thing here, and there's a common factor of dr in both terms. So we're going to pull that outside. And what do we have left? The other terms are involving all have a composition with respect to r. So we can write this as p times dq minus q times dp, all of that composed with r. So each one of these individual things is going to have an r sort of inserted where the variable is. And now we recognize, well, here's p dq minus q dp. That's looking like kind of an integral. And so we're going to introduce a new polynomial called n. It's going to be the Faulhaber integral of this thing here. S of p dq minus q dp. So this is a polynomial or a polynumber, and so we can take its Faulhaber integral, n. So what we know then is that if we take the derivative of this thing, so d of n, if we integrate and then differentiate, we get right back to where we started. So then we just get p dq minus q dp. So that means in this expression here, we can replace what's inside this little bracket here with d of n, that's now d of n, circle r. So it's 1/2 Faulhaber integral from t to u of d of n circle r times dr. But now we recognize that this is itself a derivative of n circle r. That's just the chain rule applied to this. So we reduced it to something that's an integral of a derivative, integral from t to u. So that's quite convenient. All right, so here's where we are so far. We have the signed area from t to u of p circle r, q circle r, equals 1/2 Faulhaber integral from t to u of d of n circle r. Okay, but take the derivative, then an integral like this, it's just basically giving you the original thing evaluated from the top number minus the value at the bottom number. So we get 1/2 of n circle r at u minus n circle r at t. Okay, but n circle r at u is n of r of u, because that's what the composition means. And here we're subtracting n of r of t. Now, we're going to rewrite this in this way. As 1/2 of capital S from r of t to r of u of p dq minus q dp. Because what is n? Well, n was the integral of p dq minus q dp. Okay, that's what n is. So we're taking this thing and evaluating it at r of u, and we're subtracting the value of this at r of t. So that's exactly what we mean by this notation of integral from r of t to r of u of the same quantity. Okay, but now we're in a position where we say, hey, that looks familiar. That's just the fundamental theorem form for the signed area from r of t to r of u of p comma q. And so this quantity equals this quantity, and that's the change of variables formula with a purely algebraic proof. So there's much to learn. I'm Norman Wildberger. Thanks for listening.